Module 2. So here we are at Module 2 of the 2022 paper, Analytical Methods and Separation Techniques. Mass spectrometry is a process by which the atomic mass of atoms or molecules is determined. Explain how a mass spectrometer works to obtain a mass spectrum of a molecule. There are four main ways. What's the first way? Go ahead. Number one. Okay. Okay, so there's gonna be five, my bad. So ionization, then deflection, then five, which is detection. Lovely, five, lovely. So ionization, vaporization, we vaporize the molecule, right? Ionization, no, we know what ionization is. Is the production of a mole of gaseous ions, right? So ionization is the removal of a mole of electrons from a mole of gaseous atoms to produce a mole of gaseous ions. Full stop. Then we're gonna end up with acceleration. We are accelerating the particles through an electric field, right? Going in the same direction as the surface vector of the electric field. So we're gonna be going through there. We deflection. We're going to use a mass charge ratio, right? Going perpendicular to the vector of the magnetic field B, strength B, and we're going to be deflecting the particles, right? Based on its deflection, right, we are able to detect isolated ions, right, and produce a mass spectrum, right? So we must be able to explain these. Obviously, you can't write 1 to 5 and expect to get full marks. You must explain, right? Reason why I said four is because ionization, usually in ionization, you have to vaporize the sample first. So if you say ionization and not vaporization, it is implied in your ionization example that you explain that it is vaporized particles you're actually ionizing, right? So explain them. You must be able to explain them, all right? If you have questions, you can still ask. All right, it's not just us looking at a paper and who can answer. If you have a question, ask. All right. Lovely. Let's look at the mass spectrum. Figure 3 shows the mass spectrum of a haloalkane. State the mass charge ratio of the M plus peak and the M plus 2 peak. What is another name for the M plus peak? Molecular ion peak. Lovely. All right. So what is the mass charge ratio at the M plus peak? Okay. Lovely. And we say module 2 hard. Look at that. You sure the M plus is 122 and we're sure the M plus 2 is 120 is 124? If that is the case, so what is this up here? What is this long line up here? What is that called? Okay, so let's try not to mix them up. Right? Deduce the formula of the fragment. Oh, go ahead. The base peak. Alright. Deduce the formula of the fragments of the mass charge ratio 43, 107, and 109. There are formulas that were given to you when I was going through this topic. Right? If you weren't there, then I guess you just weren't. But yeah, so there are formulas. What is it? What are the responses here? Okay. So So it's 43, 107, and 109. So 43 you said proper, what is the propyl? You said the ion. Alright, so we're gonna have a propyl cation. Right? So the first one would be a propyl cation, and the formula, um let me write out the formula instead of anything else. That would be what? It could be a propyl one or an acetyl, right? But based off of this, I think propyl would be the best response. C3H7 plus, right? That would be 43. The next one, oh my, why does 7 look like that? The next one would be what? What would 107 be? What does 107 suggest, guys? Suggest that bromine is present. Lovely. So the M plus peak, right, being at 107, right? We're looking at that. So there's some type of contaminant here. And how would we define that? How would we get to that contaminant? Are we at a loss? We're getting pretty silent now. What is it that we go through in order to get our ions? Alright, so okay, so you see 107. How do we know that bromine is present? We just see 107 and 107 means that bromine is present? How do we know? Mhm. Let's go up. About the same height as the NP. The prevalence of an M plus 2 peak, what does that mean? When we have an array with an M plus 2 peak, what that tell us? That there's a halogen present, not true? So we're saying when we have the M plus 2 peak like that, right, it shows us that there's a halogen present, right? When we're having a huge jump, we're 40, we're looking at 43, right? And then we're looking at 107 and 119, right? If we're looking at stuff like that, what we're seeing here, right, is that there is indeed some halogen present. What we need to identify now is which halogen is present. The halogen is bromine, but I want somebody to let me know what kind of bromine it is and how we arrive at that deduction. hmm So how does that relate to anything here now? What are the two isotopes of bromine? So they're about the same height. Bromine 79 and bromine 81, right? Have a 1-to-1 intensity ratio. And because it has a 1-to-1 intensity ratio, with the M plus peak and the M plus 2 peak being so close, we are the it's basically waving a red flag that is basically bromine, right? Now we know that the M plus peak is 122 and the M plus 2 peak is 124. What's the difference between those two values? 2, right? And the difference between bromine 79 and bromine 81 is 2. So we can safely assume that it is bromine being present here. Now we're called to ask, right, which bromine is present here exactly. Bromine 79. So if we're using bromine 79, what would be the structure of our component that has 107 as our mass charge ratio? So if you're minus 79 from 107, how much you have left? And then we have to work out the carbon and hydrogens after. So what is our response? C2H4 and bromine 79? Okay. So, sorry, that put boron should be bromine. Alright, so we have that there. Let me check. That would be 1, 2, 3. That would be 1, 1. Hold on, let me try it on a piece of paper here. Alright, so that would be dot 1, 2, 3, 1 bromine. And then that would be the ion. Yes, that is the ion. Right? What would 109 be? Okay. 79, you'd have the 81. Alright? So speaking to the fact that the bromine has a 1-to-1 ratio, and we're looking at it at a difference of 2. So once we look at our M plus peak here, and once we look at the M plus 2 peak, looking at the fact that it has basically a 1-to-1 ratio, and it differs by plus 2, we know that it would be similar to that. What are the two isotopes of chlorine that we would look for? If chlorine was present, what would be the ratio for chlorine? 3 to 1. Chlorine what 37 and chlorine what else? 35? So those two isotopes, I would be 3 to 1. So once you have M plus 2 peak, we must be considering a halogen. If it's 1 to 1, it's probably bromine. If it is 3 to 1, it's probably chlorine. Alright? Practice. We have to practice the questions, right? So let's have a look at this. Determine the formula of the M plus and M plus 2 molecular ion species and name the halogen. No alkane. So what is the halogen alkane? That is what we're calling for here. Are we still at, yeah, this is module 2. Scroll up. Yes. Let's have a look. Hmm. All right. So what was the structure that you said again? And the M plus two. Okay. All right. Hold on. Let me check the chat. I haven't looked in the chat in a while. So let me go and check the chat. I think this is the last paper we're doing, because this we're going into the night now. All right. So let's look at this. Alpha amino acids are found in human sweat. A student had read the chromatography, or read that chromatography could be used to separate and identify the amino acids present in human sweat. The student used thin layer chromatography to separate the amino acids, or the alpha amino acids rather, in a sample of human sweat and discovered that three different alpha amino acids were present. Name the process by which a TLC separates alpha amino acids. You sure? Solubility. Okay, so one of those answers that you just gave is definitely not right. Alright, any other responses? Because it's not only one person here now. Any other responses? What's the explanation? What's the name of the process? Partitioning and absorption, right? So the process that I would put, the best one that I would put is partitioning, right? I would put partitioning. The thing is that adsorption could work. Go ahead. Yes, it does. Yes, it does. Yes, it does. Yes, it does. All right. So partitioning chromatography is by way of adsorption, right? So it really and truly is in the same realm of things, right? So I guess the hold on. So really and truly, this would be the case. All right, partitioning or adsorption specifically for chromatography, right? Part two, the chromatogram was treated to show the positions of the separated alpha amino acids. Explain how the student could analyze the chromatogram to identify the three amino acids that were present. How would we be able to analyze that to identify the three? Hmm? No? We were moving rapid fire earlier and what's happening? Hmm. So we'd use a visualizing agent like ninhydrin, and then we would compare the R values. That's what we would do. Right? So using hydrogen staining, right, to visualize well, using as a visualizing agent, right, to attach the chromophore of the molecule so we have a bathochromic shift into the visual region. All of these chemical terms make it visible, and then we compare the R values, the retention factors. Several of the amino acids have structures that are similar. Suggest why this could cause problems when using TLC to analyze structures of amino acids. How would that be a problem? We would get what? So if they have structures that are very similar, they would have similar R values, right? And what would that do? That would lead to what? Yes, right? Would lead to overlapping, right? Spots or bands, right? So that would be a problem there. So you have if you have a very similar structure, they're going to be overlapping on the TLC plates, right? At the end of an organic reaction, a TLC of the reaction mixture indicates the presence of unreacted starting material benzoic acid, as well as the impurity of 1,4-dimethoxybenzene. Outline a series of steps indicating how this mixture can be separated and the two components recovered by the process of solvent extraction. So what would we do first? What will we do 1st? Go back up. Oh, no problem. So steps towards your question, or the 1 mark question. Oh my bad. The 1 mark question, adsorption. Mm-hmm. Huh. Okay. Okay. So okay. So adsorption. I tell you guys that I'm getting old, but the kind of separation we use is partitioning, and partitioning would be what, gas layer, gas and column, while TLC is adsorption. Mm-hmm. Okay. So, what are steps of solvent extraction? That's what the next question is asking us. We have benzene and we have 1,4-dimethoxybenzene. How do we separate them using solvent extraction? Let's go. What are the responses? The first thing we do, we wash out the beaker, right? I'm joking. But what's the first thing we do? Alright, so the first thing we do is dissolve the mixture in an organic solvent. That's true. And a good organic solvent would be what? Dichloromethane. Alright? We have that. Next thing that we can do, we can extract the benzoic acid with aqueous sodium hydroxide. Not true? If we use sodium hydroxide, we're going to form sodium benzoate, which is soluble in water. Not true. Alright? So we have those things so far. Alright? Next thing, what we do, we separate the layers. Right? So separate the layers. Right? And we can separate it by acidifying the aqueous layer to remove the benzoic acid. Right? But we can use acidification in this case. If I'm going to quickly, you can let me know. Right? The last thing we do, we evaporate the organic layer. Right? To recover basically the impurity. Why I write the impurities because I don't want to write 1,4-dimethoxybenzene. Alright? But that is it. So we dissolve the mixture, right, in organic solvent, right? And then we extract using sodium hydroxide, forming sodium benzoate, which is solved in water. And we can acidify the aqueous layer, separating the two layers there. And then we can evaporate the organic layer to recover the impurity. Alright? Specifically here. Because benzoic acid, we must know we can react the acid with a base to get a salt, which is soluble in the water and all sort of stuff. Right? So we must not just look at the chemistry, we must see what is it we require. Alright? So we have that there. 5 marks. What is meant by the term partition coefficient? Anyone? Anyone? Yes, it is. So it speaks to the ratio, right, of the ratio of the solute dissolved in the organic versus the aqueous phase. Alright? So looking at stuff like that. Now, if iodine is shaken with 100 centimeter cubes of water and 100 centimeter cubes of organic solvent, the concentration of iodine in the water layer is 4 times 10 to the negative third moles per dm cube. And in the organic solvent is 1 times 10 to the negative second mole per dm cube. Alright? So looking at this now, calculate the partition coefficient for iodine between the organic solvent and water. So we just establish what Kp is. Kp is going to be equal to the solubility in the two layers. So we're going to have 1.0 times 10 to the negative 2 divided by 4.0 times 10 to the negative 3. This is going to give us 1 over 4 is 2.5. Done. And we say chemistry hard. Both the units will cancel out. The mole will cancel out, the DMQ will cancel out. This KP has no units. Technically, it should be KD, my bad. I'm writing KP. It should be KD. My apologies. Alright, it should be KD. Alright, so looking at that now, moving now. But these are really simple. Moving on to the last question in module 2. The aqueous layer is separated and shaken with 50 centimeter cubes of a pure organic solvent. Determine the concentration of iodine in the organic solvent at equilibrium in moles per dm cube. Show all working. Now, I'm not sure whether or not that show all working is supposed to intimidate us. Alright? But let's look at this now. The initial moles of iodine in water, what would that be? The initial mole of iodine in water, what we're doing now, we have the iodine solution and we pour it into, let's look at it. So iodine is shaken with 100 centimeter cube of water and 100 centimeter cube of organic solvent, right? And we end up with 4 times 10 to the third mole per dm cube in the water layer, and 1 times 10 to the negative 2 decimeter cube, right, in the organic layer. That simply means that the initial moles of iodine in water, right, so the concentration of I2 in water initially, right, would be what? No, the multiplication. It would be the multiplication, right? So it would be the opposite of what we did. 0.4 times 10 to the negative 3 times 0.1, right? Times 10 to the negative 2. How much that? Can anybody tell me how much that is? I don't have a calculator with me. Can somebody just give me that? Let's see. Would that be 4 point? 10 to the negative 2. Yes. Negative 6? Hmm. Hmm. Why it feels like something is going to be off today. Hold on one moment. So the iodine in the water and 50 adults. Fine. 0.1. Okay, let's see what value we get for this answer. Times 10 to the negative 6. Let's see what we get for this. Alright. So we're going to look at this now. We're going to be solving for x. Alright, but I'm going to see if I can build this equation first. So solve for x and find the concentration in the organic phase. Alrighty. So we have 50 per centimeter cube. So the aqueous layer is separated and shaken with. Okay, it's the aqueous layer. So the aqueous layer is taken and shaken. Right, separated and shaken with 50 centimeter cube of pure organic solvent. So we're going to end up with the same partitioning as before. Alright, so we're gonna look at KD, which is equal to, our know is 2.5 from above, which is equal to now whatever value x, right? That is the concentration we're looking for, divided by 0.05, which is the 50 centimeter cube that we have. And all of that now is divided by 4.0 times 10 to the negative 6 minus that condition there, right? It must be divided by what now? Hold on. This is 100. This would be 0.1. 0.1. Alright, so I made a mistake right there. So it actually should just be multiplied by 0.1, right? And that would give you to the negative 4th power. And then this would just be now divided by 0.1. Go ahead with the question. I think somebody raised their hand. Great question. Does anybody have an explanation for that? There are at least 48 other persons in the meeting. Does anybody want to have a go at explaining why that is? No. All right. So the aqueous layer, right? So let's look over the question one more time. All right. So the aqueous layer is separated and shaken with 50. Right. So what we're saying here, we took the iodine, right, initially in the first part of the question, and we shook it with actually 100 centimeter cube of water and 100 centimeter cube of the organic solvent, right? So we basically did that. That's the first part of it, right? Do we understand what that means, right? And then after that, no, the aqueous layer is separated off. So whatever is left in the organic phase is left in the organic phase, right? We'll only take the aqueous phase. So that's 1.0 times 10 to the negative 2 moles that is left in the organic phase. And now we take up now the aqueous phase alone, right? And shook it with now 50, right? Centimeter cube of pure organic solvent. So use fresh organic solvent now. What we're called to do now is determine the concentration of iodine in the organic solvent at equilibrium, right, in mole per dm cube. So we're trying to figure out how much is dissolved there, right? So that's the first part or the first aspect of the entire question, all right? So we just need to try to understand what's happening there, and then I can go through what we're doing. So does that make sense so far? Do we understand what we're doing? Let me check the chat. Nobody has an explanation for this? Let me check the chart real quick because I'm not sure if we're following in the first place. So we're minus the x because of the pure organic layer, alright? Because we've lost some of it in the organic layer. So that has been completely removed from what we have, alright? And then we're now trying to find how much of that is there. So remember that the numerator is the organic phase, and the denominator is the aqueous phase, right? We're trying to find X that is dissolved in the organic phase. And so in the aqueous phase, we're trying to minus that X here. What we're trying to overall do now is solve for X in this case. And once we solve for X, we have found our answer. Alright? So it's just up to you to solve for that. So I'm going to give you guys a moment to just quickly go through that. And we should be able to be fine. Alright? Just quickly solve for X and let me know what your values are, what your answers are. Any responses so far? Have we found it? Or are we tired? How would you define X? Alright, so I'm not receiving any. Let me check the chat real quick before I say anything. Go ahead, Divine. Yes, it's going to be a very long process. So, hmm, we still need to do it, not true? We still need to do it. Alright. So we're gonna multiply everything here by 0.05 over x. Alright. So let's have a look at this. 0.4 times 10 to the negative fourth power minus x over 0.1 times 0.05 over x. Right? So we're working with that would now give us 2.5 is equal to 4.0 times 10 to the negative fourth power minus x times 0.05 all over 0.1x. Right? We now multiply both sides by 0.1. This is going to look a little bit messy. Not sure where is the best place to put this, but when we multiply both sides by 0.1, we should end up with 0.25 is equal to 0.05 times that 4 times 10 to the negative fourth power minus x value, right? And we should end up getting 0.25 is equal to 2.0 times 10 to the negative fifth power, right? Minus 0.05x, right? From that now you can solve x, because x now will be equal to what? 2.0 times 10 to the negative 5 divided by 0.30, which would give us 6.67 times 10 to the negative 5 moles. Alright? But I may have to represent that in a different way or something to you guys. Alright? That would be the number of moles, and then we take that now. We'll take that, plug it in as x, and find 3.33, I think, times 10 to the negative 3 power, which is really and truly the answer. But we'll have to work that out some time. Yeah, it's a lot. This is not even half of the question. There's more to it. Um, but really and truly, the rest of it is math. But go ahead. This paper was all right. Let's move on. But the thing is, the rest of it is math, right? Your response should be the concentration of the organic phase should be around 3 point something. All right, times 10 to the negative 3, I believe. All right. But the rest of it is math. You just need to